Yeah, hello everyone. My name is Mehdi. I'm a co-founder and director of Sigma Prime. We are going to talk about Solidity and EVM security today. So Sigma Prime is an information security consultancy. We're mostly based out of Sydney, Australia, even though I'm currently in Berlin for the Blockchain Week. And we're basically a collective of security researchers, engineers, and academics who got together about 3 years ago now to work on secure and decentralized solutions for our society. I've listed a few of our clients in the information security space. You're probably familiar with some of them, and very, very happy to have Dapper Labs as our client, who trusts us with their smart contract security assessment requirements, which is something I'm particularly proud of. So that's the reason why we're doing this, and we're part of this global hackathon. So there's a lot to cover. We won't have time to cover all the attack vectors, all the possible vulnerabilities in Solidity, so feel free to hit me up if you have any questions during the hackathon, during the development process. More than happy to assist. Another thing that Sigma Prime does is maintain and develop the Rust implementation of Ethereum 2.0, or a Rust implementation of ETH2. It's called Lighthouse. Started about a year ago now, and it's in Rust. We love Rust, and so we're working really hard to hopefully bring you a proof of stake sharded blockchain, hopefully very, very soon. So that's Sigma Prime in a nutshell. I'm going to take some time to talk about some EVM basics that I think are very, very important to understand and get our head around when we deal with smart contracts. And then we'll dive into the main topic and address all the vulnerabilities that we know of, or at least a subset of them, and how to counter those. And I'll try to give real life examples of how those vulnerabilities were actually exploited, and how hackers actually managed to either permanently DOS smart contracts or even steal user funds. But first, we'll talk about the EVM very, very briefly. So it's a sandboxed VM. So it's a stack machine. Every Ethereum node is effectively running a sandbox with that virtual machine. So this diagram basically tells you where it sits within the stack. At the very, very bottom, you've got your standard x86 ARM processor, which support the Ethereum and Ethereum node, be it Geth, Parity, or Pantheon, or Trinity. And each of these nodes runs a sandbox virtual machine on top of which we deploy and execute EVM code. Smart contracts are basically just bytecode that's stored at particular addresses. Those addresses are deterministically generated based on the address of the contract deployer and the nonce associated with that account. And when we talk about smart contracts, we usually refer to the sort of source code that's written in a higher level language. So most of us here know of Solidity, but it's not the only one. It's not the only language that compiles to EVM. Before Solidity, people were writing in Triple L and Bamboo, for example, and Viper has been taken off lately with the deposit contract for the ETH2 transition being written in Viper, for example. So we'll focus on Solidity in today's talk because it's what most people use, and I expect it'll be around for a while. Even when we move away from the EVM to EWASM, a lot of people have invested in Solidity and Solidity developers, so there's ways to basically transcompile to EWASM from Solidity. And in Solidity, you can use inline assembly, right? So inline assembly allows you to have a fine-grained access to the stack, the memory, the storage, but you really have to use it at your own risks, in the sense that it's very, very easy to mess things up when you operate at a lower level. Solidity, a lot of people, it's a love and hate relationship with Solidity, but it does come with a lot of security properties that you can completely bypass if you're using inline assembly. A lot of clients of ours use inline assembly for gas optimizations, gas savings, but it comes at a risk. And that risk, I guess, is messing things up, particularly when you're reading from memory or storing in persistent storage. So as I said, these languages, they all compile to EVM bytecode. So I've got a very, very simple example of a smart contract which has one state variable and two functions, a setter and a getter. So that's what the actual runtime will look like. That's if you were to deploy this smart contract on chain. This is exactly what will be living on chain. Very, very important to distinguish the two types of accounts that we have today. This may no longer be the case with upcoming hard forks, potentially scheduled for either 1x, ETH 1.x, or also ETH2. But as of today, there are two types of accounts. You've got your externally owned accounts, or EOAs, and you've got your contract accounts. So EOAs are basically the accounts that you use when you manipulate, when you have your Trezor, your Ledger, your MetaMask, your paper wallets. They basically have a private key associated to them, and this is what allows you to move Ether or send transactions from that account. Contract accounts are very different in the sense that they don't have a private key associated to them, and they're governed by the code and the storage that these accounts have. So you can see them as autonomous objects. What defines an EOA in the world state? So in the Ethereum yellow paper, there's this definition of the world state, which is sigma, and we apply state transitions to it, which gives us sigma prime. This is where the name of the company comes from. Essentially we have for EOAs only sort of two things that define an EOA. So you've got obviously your address, which has a nonce and a balance. Okay, and as I said, these accounts are controlled with a private key. Then you've got your contract accounts, which has the same address, which is tied to a nonce and a balance, but also a storage, which is defined by the storage hash at any time, and a code, which is defined by the code hash, right? So clear distinctions between the two, very important to keep that in mind. The EVM is somewhat very different from other virtual machines that you may have played with in the past. So particularly like if you've done any Java, you've got your Java virtual machines, which are usually, they're register-based machines, and there's no such thing in Ethereum. We call them this pseudo register. Everything happens on the stack, and we'll see the difference between stack, memory, and storage in a bit. The EVM defines a set of opcodes, right? So Gavin Wood in 2014 formally defined what opcodes will be implemented by the Ethereum nodes and Ethereum clients. And you've got your standard arithmetic operations, so your subtractions, multiplications, additions, divisions, and stuff like that. You've got your bitwise operations that can come in very, very handy. You've got ANDs, bit ORs, and XORs. And then your standard memory operation, so pushing, popping, storing, loading, and things like that. So that's kind of very, very similar to the virtual machines that we know, or the opcodes in like the standard legacy world. But the following ones are very specific to Ethereum. So you can always fetch block-specific information using opcodes such as gas limit, or number, or gas price. These are very specific to Ethereum and allows developers to essentially fetch context-specific and block-specific information for their smart contracts. And obviously, as for any blockchains, cryptography is very important, and cryptographic functions are used a lot. So SHA-3, or hash, has been modeled and implemented as an opcode, as a dedicated opcode, which can come in very, very, very handy. As I said, there's no registers in the EVM. Every instruction is invoked, and even the parameters are passed by the EVM stack. We use 160-bit addresses, something you probably know already, and there's this very interesting concept of logs or events in the EVM that allows us to store data without actually storing it on-chain. Right, so we can emit events. These events will be stored on all the Ethereum nodes, but they won't be stored on-chain. So it's one way to essentially save gas when dealing with data storage. So, which leads me to the next concept of gas, which is extremely important, which was introduced with the yellow paper and allows us to essentially prevent denial of service attacks. So every single opcode has a cost associated to it, and that cost is expressed in gas. We'll just dive very quickly into what stack, memory, and storage are. So the stack, as I said, is this very, very volatile memory. You've got 256 bit words, and you've got up to 1024 elements. And as all the operations are performed on the stack, you need to access those words very quickly, and you use things like push, pops, copy, and swap. And that's kind of similar to how x86 machines sort of operate. The memory is also a volatile memory. It is cleared for each call. Each message call will have we'll start with a fresh memory, with a clear memory, and the opcodes associated to it are mload if you want to read, and mstore if you want to write. It scales quadratically, which means that the more memory you need, or the more memory you manipulate, the more expensive it'll get. And last but not least, you've got your account storage. This is your persistent on-chain storage mechanism, which essentially allows us to have a key value. We can see it as a key value database on-chain. So your keys are 256-bit words, and your value are also 256-bit words. So it is, for a very good reason, very expensive to write to it, but also expensive to read from it. So if you were to manipulate this, so my example, what I had earlier, a stored data integer is essentially stored this way, where I've got my key here, which will be in this case 0, and my value here, which will be whatever value I set it to. It is, as I said, very costly to read and very, very expensive to write. If I'm not mistaken, it'll be 20,000 gas per 256-bit word off the top of my head. So that's something you don't want to do too often, and you only really want to do when necessary. Another important part of the EVM, or the Ethereum development, is what we call application binary interfaces, or ABIs. These are standard ways to interact with a smart contract. You deploy a smart contract, it's got a bunch of functions. How do I actually speak to it? How do I interface with it? Well, this is where the ABI comes into play. You basically can generate an ABI based on a Solidity file, which gives you a list of the functions available and the expected types of parameters that you need to submit in order to interact with them. That's extremely important. Without this, we wouldn't be able to actually interact with those smart contracts because they're not self-describing, right? Like every single function can take a different type of parameters. So that's also quite crucial to understand. Last but not least, function signatures are how we tell smart contracts which function we want to hit, and that's at the sort of low level. When you make a message call, when you make a call to a smart contract, you are passing it a function signature. So the transfer function for an ERC20 token, for example, its signature is transfer address and UA256. So basically, name of the function and the parameter types that it takes. And then what happens is that we take the KKAK hash of this function signature, and then we take the first 4 bytes, and that gives us the function selector. And that's what we pass at the very low level in the EVM call stack to the smart contracts. Hope that makes sense. If there are any questions at this stage, I'm more than happy to take them. Otherwise, we'll move on to the main sort of topic: how developers usually screw up their smart contracts, and how we can identify pitfalls and attack vectors.
I don't have any questions.
Cool, awesome. Moving on to the next section then. I'm gonna, as I said, list a bunch of vulnerabilities. Don't have the time to list them all, but I'll do my best to. We've got a bit of time, so might as well cover as much as we can. one thing that is no longer sort of applicable is this vulnerability, but I thought we'd touch base on it because it's still quite important to understand what's going on when you mess up your visibilities. So this smart contract wouldn't actually compile today as of Solidity v0.5 because you have to specify, you have to declare your visibility explicitly. So in this example, we have a function which is withdraw winnings, and the purpose of the game is to have a user generate an address, an Ethereum address that ends with 8 zeros, right? The last 8 hex characters are 0. And if that's the case, so message.sender is indeed ending with all these zeros, then we call the subfunction send winnings, right? Which basically effectively transfers the balance of the contract to allegedly the winner. What happens here is that because we didn't provide visibility, these two functions are callable externally. So anyone can call directly send winnings, right? And defeat the whole purpose of the game. So this may sound really sort of stupid, but it happens. And unfortunately, we lost more than $30 million to a hack like this. So Parity, the first Parity multi-sig hack, is exactly what happened. The developer forgot to provide a visibility to the init wallet function, which was basically called externally by someone to essentially reset the ownership of the wallet, and that resulted in $31 million of Ether back then, stolen by this attacker. So back then, again, everything defaulted to public. So anything that you don't declare is public and publicly callable. But as of now, it's no longer the case, and this contract wouldn't actually compile at all. But it's very important to keep in mind that you don't want to expose too much, right? If a function is not meant to be called externally, do not declare it public, right? Public is sometimes seen as a lazy way of declaring stuff. Think about the implications of having a function be public, right? It means that anyone can call it. And if you don't have the right modifiers, if you don't have the right restrictions, this can have catastrophic results. And as I said, the real life example is one of the first hacks, or the first multi-sig wallet hack from Parity was something that really happened in real life. It may sound really easy and stupid, but again, we all make mistakes, and I guess we're here to make sure that we make as little mistakes as possible. Another interesting type of vulnerability that we actually find quite a lot in our audits is when you deal with floating points and precision in Solidity. So Solidity does not have fixed points. I've added the yet because we've been promised to have fixed points for a while now, but I'm not sure it's actually ever going to happen. But it's fine because there are ways to prevent that. So what's happening in this contract, we have a buy token and a sell token function. And what we're doing is we're computing the number of tokens based on the amount of Ether or the amount of Wei sent by the buyer, right? So what's going to happen here is that if the value of the message value or the value of the Ether sent in that transaction is less than 1 Ether, what's going to happen is that when we divide message value with this number, we're going to get 0. Right? Because we're always rounding in Solidity. So in this case, the buyer will send, let's say, 0.8 Ether, expecting some tokens. What's going to happen is that his balance will effectively be set to 0, or stay at 0. And same thing with the selling function. If we try to sell less than 10 tokens, well, the resulting price will be 0 Ether. So how do we deal with this? Well, it is fairly simple. You should essentially keep in mind the order of the operations and try to have divisions at the very, 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 very last. So what you want to have is large numerators in fractions, right? So in this case, instead of using tokens per Ether, I don't think you guys can see my mouse, but the first constant state variable declared, instead of using tokens per Ether, well, we should be using Wei per tokens. Right? In this case, if we were using Wei per tokens, then our numerator will be, big, right? So when dividing, the rounding factor won't have as many implications, many it wouldn't be as bad as what's just happened in this example. So the blue sort of way of doing it is the right one, because as I said, you're dealing first with your multiplication, which will result in a large number, and then your division, as opposed to the opposite. If you really want to use floating points, there's a couple of libraries out there that you can use. One of them is DSMath from MakerDAO. I haven't, I said safe libraries, but I haven't audited them myself. But I know that a lot of projects in the ecosystem rely on them, including MakerDAO, which has now 1.5% of all Ether locked in. So probably safe to assume that these libraries are secure. Hopefully that makes sense. I'm going to move on to another type of bugs, which is quite interesting, and it's not something that's actually specific to Solidity or to the EVM. It's what we call overflows, right? Overflowing integers, underflowing integers. If we take, for example, a uint8, that allows us to store numbers from 0 to 255, right? So it's basically 0 to the power 8 minus 1. Anything above that will result in a loop. You're looping back to the start. So if I'm trying to store 257 on a uint8, it will result in 1. And you can think of it as, for people who like math, trigonometry, right? Sinus and cosinus, right? It's like this counter, you always go back. So sinus of x is the same thing as sinus of x plus 2 pi. Same with cosinus, right? So that's something very important, especially when dealing with large numbers, right? So there's countless examples of things that went wrong in production, smart contracts due to underflows and overflows. I've got this example right here where if you can see the this check in the transfer function in line 13 will always be true, right? Because of the overflow that I explained, because we're dealing with unsigned integers, and then these unsigned integers will always result in this subtraction will always be positive. So how do we deal with this? Well, thank God we've got OpenZeppelin to the rescue, and Safe Math has been developed by our friends from OpenZeppelin, and is being used in a lot of projects, right? So Safe Math allows you essentially to replace your standard operators with a safer way of dealing with additions and subtractions and multiplications. What happens is that we're basically checking the bounds every time we make an operation, and if we are to overflow, we just revert, right? We've also seen a lot of people not use it, because this comes at a cost, at a gas cost, obviously, and it's essentially something that you should be very careful with. That's something that we've raised multiple times. It's usually advanced smart contract developers who think and believe that they can rely on their own calculations to prevent overflows, but you just have to be extremely careful. Oh yeah, and an example of a real-world smart contracts that got popped with this vulnerability is the proof of weak hands coins. I'm not sure if you guys remember, that was, I think, last year. This 4chan group of people decided to have this Ponzi scheme. It was literally a Ponzi scheme. It was not trying to hide the fact that it was a Ponzi. And more than 850 Ether were stolen. And I've just highlighted the line that's basically responsible for this underflow. And hopefully you can see it. We're multiplying the this sort of the length of this array with a value, and we're basically again looping back to where we should start from. So these are real life bugs again. These aren't theoretical vulnerabilities, and they are being exploited every time. And there's now bots that will scrape either scan and scrape the blockchain to automatically detect these potential overflows and just automatically exploit them. So if you are to deploy a smart contract with a vulnerable implementation of mathematical operations, chances are it'll be actually exploited within a few minutes. So be extremely careful when dealing with math operations. One of my favorite vulnerabilities is this one. What we call a Sigma Prime unexpected ether. So a lot of people, a lot of developers assume that the contract's balance is an invariant, right? Unless I send ether to it directly with a payable function, the balance should not move. So a lot of checks can be, or unfortunately are, relying on this poor invariant. And why is it a poor invariant? Because there are two exceptions to the rule that people or developers have in mind, which is having either the fallback function or any other function that's payable receive ether. That's true, but not entirely true, in the sense that there's two ways to send ether to a contract without actually calling any function. The first one is by creating a contract, self-destructing, and sending the balance of the contract, attacking the contract, to another contract. This will increase the balance of the vulnerable contract without actually calling any function. So that's one way to do it, with the self-destruct opcode. And the other way to do it is to pre-send ether to it. So remember earlier on, I said that the contract address is deterministic, right? So I can basically, if I know which account will be deploying a contract and what the nonce will be at the deployment, then I know exactly what the address will be, which means I can send ether to this address in the future, right? So I can send ether to this address, and when the contract will be deployed, it'll automatically have this new balance associated to it. So that's quite interesting when you think about it, and there's a lot of ways to avoid that, but mainly don't rely on the contract balance as an invariant. It is not invariant, and people can mess with that and change it as they really want. And I'm not sure if you guys remember, but I forgot the name of the contract. I have it written somewhere, hopefully. Edgeware, yeah, Edgeware had a vulnerability a few weeks ago, and it was exactly that. It was exactly that. It was relying on the contract's balance as invariant. It was extremely easy to prove that invariant wrong, right? By using one of the two options that I described. Yeah, I've got an example here where we require, it is here. Yeah, so the current balance is this.balance plus message.value. But if we rely on this.balance, well, we are not actually, there's a way to lock this contract permanently by sending it either, be it with the self-destruct method or the pre-computed contract address method. Yeah, what we should be doing, as I said, is just not using the contract balance as an invariant and defining a dedicated state variable that you will use to keep track of your account's balances, essentially. Cool. Another cool vulnerability that we find very, very often in our audits is the fact that entropy is extremely hard on-chain. Not only it's hard, it's almost impossible, right? So every blockchain, Ethereum, Neo, you name it, is basically a deterministic state transition model, right? So be given a certain state, given a certain input, we know exactly what the output will be. What this means is that there's no randomness in Solidity. There's no way to have randomness in Solidity. That's something we have to accept. And when we're dealing with games, when we're dealing with lottery, it becomes a problem. How can we achieve decentralized entropy, which is a source of randomness, is something that has been researched for years now. One way to do this is by having a commit and reveal scheme, right? And when you have a commit and reveal scheme, you're basically relying on off-chain randomness, off-chain entropy. You want to have your participants provide entropy to your smart contract, basically to essentially work out how to compute a random number, how to guess a random number. So a lot of common pitfalls would be relying on hashes, right? I'm going to use the previous block number. I'm going to use the previous block hash. I'm going to use the previous block timestamp. That's obviously cannot work, right? Because I can always deploy a smart contract which will have access to this information, and they will make a bet accordingly, and then your entire lottery game will be flawed. Another problem that we've noticed was using a seed and flagging it as private, right? So declaring the seed as private in your smart contract code does not make it private. It just makes it hard for developers, hard for users to read, because we don't have Solidity won't essentially give you getters for that function, for that variable, sorry, but the variable is still on chain, right? And it's very, very, very easy for advanced users or hackers to retrieve that information. So again, the fact that you declare a variable private does not make it private in the sense, confidential. One way to do it, as I said, is a commit and reveal sort of approach. Commit and reveal schemes are extremely popular. We use them in all sorts of different smart contracts. ENS is one of them, the Ethereum name system is one of them, and Cheeze Wizards as well, right? Cheeze Wizard is a commit and reveal game, right? You're committing to a certain moves, you sign your commits, you provide the hash on chain, and then you reveal it later on. So it's very well documented. We now understand the risks of commit and reveal schemes, and one of them is replay attacks. So I don't necessarily have the time to go through what replay attacks are in this particular context, but look them up. They're very easy to mitigate, usually by having a salt, right? Like this extra bit of information that needs to be revealed as well. Hopefully, entropy will be solved. On-chain entropy will be solved with VDFs, verifiably delayable functions. So you may have heard that the Ethereum Foundation is looking at having VDFs for the beacon chain. VDFs are very recent cryptographic sort of advancement in the world, and Ethereum would potentially be one of the very first projects to use them, and they're quite exciting because they now allow us to have this source of entropy on chain that we can use not only for shuffling validators and assigning them different tasks, but we can also use them for smart contracts. So our smart contracts will then be able to pull randomness, pull entropy from those VDFs, which will make games like blackjack or roulette actually fair and fairly easy to implement in a secure way. So very excited about that. It should hopefully be live within 18 months to 24 months. And there's heaps of problems with pseudo-random generation. And I've got this great blog post that essentially scrapped the Ethereum blockchain, and yeah, that was a little while ago. So I'm assuming there's a lot more vulnerable contracts out there. Race conditions and front running. That's something that I'm sure a lot of you guys have heard of, especially in the context of decentralized exchanges. Phil Diane produced a paper a few months ago, which is extremely well written, that explains exactly how malicious users can monitor the blockchain and essentially take advantage of certain transactions, of seeing certain transactions on the network. Consider this smart contract where you need to find the string that effectively generates this hash. So what we're doing, we're just requiring with the on line 8, we check that the SHA-3, the KKK hash of the solution provided, is indeed matching the hash that's declared as a constant. So, and if that's the case, then we send 1,000 Ether to the person who solved effectively this puzzle. Well, if you were to actually play this game, chances are you'll be front run, right? The only thing I need is to listen to the blockchain, listen to the mempool, the transaction mempool, and see that I have this transaction incoming. And what I'm going to do is I'm just simply going to send the exact same transaction with effectively a higher gas price. And I don't need a greater gas price. Like, we've seen bots just essentially adding 1 gig away to the gas price that they're trying to front run, of the transaction they're trying to front run. And it's extremely, extremely hard to prevent against that. And that's why a lot of games are inherently impossible to win, because you're effectively going to be racing against bots, and these bots will always win, right? Because the only thing they do is replay your transaction with a higher gas price. So how can we do this? How can we ensure that we're deploying games, we're deploying applications that are fair for everyone to play, that are front-running, you know, basically resilient? Well, there's a few ways to do it. We can essentially create upper bounds to the gas price and be like, my smart contract will not accept any transaction with a gas price higher than X. And we've seen this a lot in the ICO craze, where everyone wanted to sort of get in those token sales, and some of those contracts were saying, no, any transaction greater than, with a gas price greater than 20 gigawatt or 30 gigawatt will not be processed by a smart contract, literally having a require statement on the gas price of the transaction. And then another way to play it would be to have a commit and reveal pattern, right? So you can commit to a certain result and then reveal it later on, so that there's no way for the bots to actually front run you, right? Bancor had a pretty bad front running vulnerability, and the ERC20 is something people actually, not many people understand, is that the ERC20 standard is inherently vulnerable to a front running in the approve method, right? So if I approve someone to spend a certain amount of tokens and then they change their minds, they lower my approval sort of limit, then if I see this happen, I can spend that approval limit twice, right? I can spend it before their transaction hits, which makes it, let's say, they allow me to move 10 rep on their behalf, and then they change their mind, and they send the transaction to adjust that limit to 5 rep. What I do is I'm going to see that new transactions of 5 rep, of approved 5 rep, and I'm going to spend the 10 rep first, and then be granted another 5 rep, right? And there's no way to fix this inherently, or there are a couple of ways that we can mitigate it, but it's inherently the standard itself that's affected and flawed. Another, what time is it? Okay, I got a bit of time. Another way that I think smart contracts developers can screw up, and hopefully this is no longer the case, because there's been a lot of noise being made around this particular issue, and a lot of developers are now aware of this concept of transaction.origin. So transaction.origin effectively propagates and goes all the way through the call stack, as opposed to the message.sender, which changes every time the caller changes, right? Except for delegate calls, and we'll talk about delegate calls later. But in the concept of standard calls, normal calls, transaction.origin gets propagated, meaning that my externally owned account interacting with the smart contract will be the transaction.origin. The address of my EOA will be the transaction.origin. So what happens is that if we use transaction.origin as a way of authenticating who's allowed to access or interact with our smart contracts, then we become vulnerable to phishing attacks. Consider this contract where we have a withdraw function that essentially checks that the transaction.origin is the owner of the contract. What I can do is create a phishing contract, right? And be like, hey owner, please send the transaction to this contract in order for you to get 1 Ether. If you send me a transaction to this contract, I can give you 1 Ether. And what it does, it is basically its fallback function. It will call the phishable contract, right? And it will call the withdrawal with the attacker's address. And what happens is that this require will then pass, right? Because the originator of the initial call is the owner, right? The owner is interacting with us, but it's effectively sending a call to the withdrawal function, and voila, that's it. That's all we need to do. We just need them to send 1 transaction to this contract. And there you go. All the Ether available on this contract is now ours. So hopefully you can see the dangers of using transaction.origins as a way of authenticating your users. You should not do that because you are now exposed to phishing attacks, and phishing attacks are fairly easy to implement, and with the right social engineering techniques, we can always get people to click on stuff and do stuff. If I promise you 1,000 ether by sending, or a 10 ether, you'll probably do it, but you won't actually know that what I'm after is the 100 ether that you're entitled to on a different contract. So one way that we can use transaction.origin to basically forbid contracts from interacting with contracts is by requiring the transaction.origin to be the same as message.sender, right? If message.sender is different from transaction.origin, it is safe to assume that the call has been made, the last low-level call has been made by a smart contract and not an EOA. Hopefully that all makes sense. Probably the last one I have time to cover before we move on to questions is the denial of service type of vulnerabilities. So in this example, we have an array of investors, right? This line 4, an array of UID256. UID is actually an alias for UID256. Yeah, we've got this array of investors. Every time someone invests, we add to the array. I think, does someone have a question? Because I can hear. Maybe Max, if you don't mind going mute. Sorry, I can hear my voice. That's all right. So yeah, as I said, every time an investor sends ether to this contract, we're increasing the size of the array, right? And what's going to happen when someone calls the distribute function, or when the owner calls the distribute function, we're looping through every single instance, every single element of this array. At some stage, we will hit a we're going to run out of gas because we won't have enough gas to actually go through every single array. And what's going to happen is that some investors will miss out. Some investors won't get their tokens because they're too deep down the actual stack in the array. So yeah, so that's another type of denial of service attacks or denial of service challenges that we see often in smart contracts. When the whole architecture or the whole logic of a smart contract relies on one address, which is the case of this smart contract, right? If the owner is incapacitated, it does not, let's say the owner lost its private key, right? That private key is now gone. This contract is now useless because we can never finalize it, right? So it's extremely important to be very, very, very careful with this type of denial of service conditions. Always, have either multi-sig wallets with proper backup mechanisms, or have a time lock. Like, everyone can unlock this contract after a certain amount of time, right? So that if something happens to the owners, shit happens, right? It always can die or lose their private keys. Then you're not relying solely on the existence of the private key associated with one account to operate this contract. Probably can talk about re-entrancies. So re-entrancies came in and were very, very famous thanks to the DAO. Not sure if a lot of you guys were in the space back then. I think everyone who was remembers exactly what they were doing that day. I was attending a talk at Google in Sydney and had to leave because obviously I was had some DAOs, and what happened that night was pretty epic. And it all happened because of re-entrancy vulnerability. So it's not so trivial to understand, but I've got an example here. So consider this smart contract, right, which has a deposit fund function and a withdraw funds function, okay? So what we're doing here is that we're sending funds to it, and that's how we're increasing our balances on the smart contract. And then we can withdraw those funds at some stage with a line 17, where we're requiring the call value to be worth a certain amount of weight. My attack contract here is essentially gonna re-enter by calling the withdraw funds multiple times. So what happens, so sorry, just go back here. Yep. What happens when I withdraw the funds is that we're basically instructing the contract to perform a call function on this address that is effectively calling the contract. So if I have a malicious smart contract that I use to call withdraw funds, and then withdraw funds itself makes a call on this smart contract, which will effectively hit the payable function, sorry, the fallback function. This is where all the magic happens. And what I'm doing is that as long as the store's balance is 1 Ether, I'm calling withdraw funds again. So I'm basically stuck now in this loop, draining the contract out of its Ether, because as you can see, the checks, or sorry, the state changes happens after the call, right? So I'm always going to be, these two conditions will always be true because I'm not changing the balance of my caller at the right time, right? So I'm constantly, with this attack contract, I'm constantly re-entering and draining the user's funds or the contract's funds as long as its balance is more than 1 Ether. And that's exactly how a lot of Ether was stolen from the DAO. That's how, you know, Ethereum Classic came to existence. And there's a few ways to mitigate it. So one way is to use transfer and send functions, which are by definition limited in the number of gas they can use. Only 2,300 gas, which is just enough to log an event, right? If I use transfer, I can't re-enter because re-entering will, you know, cost a lot more than 2,300 gas, and this will lead to a revert, essentially, will revert the transaction. We also want to make sure that all state changing code happens before Ether is sent out, right? So when I change the balance of my contract here, sorry, the balance of my caller, this should happen before we actually send them the Ether. It's what we call the interactions pattern, and you want your interactions pattern. Checks, effects, interactions pattern. So you want checks first, effects, and then interactions. And it's very, very important to keep in mind. And unfortunately, Solidity or the EVM itself does not prevent us from these mistakes. We have these are design decisions. So developers are responsible for essentially these bugs, and can't rely on the compiler to pick them up. Can't rely on, you know, the EVM to prevent us from introducing these problems. One other way to do it is to have a mutex. So you've got a lock, like you can see it as a state variable that's true or false, and then every time we have a withdrawal, we lock it, meaning that we can't re-enter again. And then once the withdrawal is done, we unlock it. So that's one way to do it, but it's fairly expensive gas-wise because it forces you to introduce an additional state variable and to maintain it and change it every time there's basically a state or a call being made. Then we've got the static calls, and these are pretty handy because we're using them, or Dapper Labs is using them quite extensively in Dapper and Cheeze Wizards as well, in the sense that we're preventing any state changes, right? If you have a view function, you know for a fact that there shouldn't be any state changes associated with that function, then just make it a static call. And as I said, real world example is the DAO, and there's been lots of great write-ups, and I encourage you all to go through it and understand exactly what happened. It's quite fascinating. Unfortunately, don't have time to go through the delegate calls, but the slides will be available. And if you have any questions, please feel free to hit me up. As I said, there's a lot more vulnerabilities, can't cover them all. We have a blog post hosted by Sigma Prime, so Solidity Security. This is the sort of Bible of Solidity Security. So you may have heard of Mastering Ethereum by Andres Antonopoulos and Gavin Wood. This blog is effectively the smart contract security section of the book. So Andreas and Gav reached out to us, asking us if they could use this content for their book, which obviously we agreed to, and we're very, very happy and proud to have contributed to this book. So feel free to look at it. It's on our blog. It provides a lot of details on how to mitigate those vulnerabilities, how to avoid them in the first place. And if you want to get your fingers dirty, if you want to practice smart contract security and breaking and hacking smart contracts, highly recommend the Ethernaut challenges deployed by our friends at OpenZeppelin. They're in sort of ascending difficulty. The first ones are very simple. The final ones are pretty tricky, and we've contributed, I think, 7 or 8 challenges. So some of those challenges are really pricing. And that's it for me. There was a lot of talking. If you guys have any questions, please, it's now. Otherwise, you can always hit me up on Twitter. That's my handle. Or you can also send me an email throughout the hackathon. I'll be more than happy to help you make the right design decisions for your smart contracts in terms of security implications. And the winners of the smart contracts will have the opportunity to engage Sigma Prime for an audit of their solution with a very preferential sort of rate. So we're giving substantial discounts to the winners of the hackathon. Thanks for your attention, guys. I'm happy to take any questions now.
Thank you, Mehdi. That was awesome. Like really informative and like laid out so that I can understand.
Awesome. Glad it was useful.
All right. So then you said if you know the contract, if you know the address about someone who's going to deploy a contract and the nonce, that's all you need to understand, like how to deploy some sort of like counterfactual address contract. Sorry.
Yeah. Absolutely.
Oh yeah. And then do those like the smart contracts that you use as wallets, like smart contract wallets, do they use the TX.ORIGIN method, or is it in some of their functions?
Yeah, that's a very good question. So I'm just going back to your first point. Okay. This is how you compute the address of an actual contract. Yeah, sorry. So you have your account address, you have your transaction nonce, you RLP encode them, and that gives you the address of your smart contract. So it's very deterministic, meaning that if I know the nonce, if I know the address, I can compute what the contract address will be. And to go back to your second question, if you're referring to wallets such as DAPA, for example, DAPA will maintain internally its own access control mechanism. Others, such as Gnosis Safe, will do it similarly. But if we're talking about DAPA, for example, I guess we can talk about DAPA. It's a Cheeze Wizards Hackathon after all. We were maintaining this set of authorized addresses that are allowed to interact with the smart contract. So, and what we do is we use delegate calls, right? So I'm invoking functions, and those functions, as an end user, will then call the functions that are the smart contracts that I'm targeting on behalf. All right.
Yeah, you cut off for a bit there, Mehdi, but.
Oh, sorry. Sorry. Do you want me to repeat? Which part do you want me to repeat?
Which part did you leave off at? You're talking about. Yeah, you have a designated list of addresses that can access that smart contract.
Yeah, exactly. So it's got its own set of authorized addresses. So in the case of DAPA, the DAPA wallet, you can have a signer and a co-signer, right? So in case we need a co-signer, then the contract will require you to submit 2 signatures, the signers and the co-signer. In the case the co-signer's address is equal to the signer address, what this effectively means is that we don't have a co-signer, we only have a signer. and then we actually don't even need to submit a signature. The signature is directly taken from the transaction, from the Ethereum transaction, right? So you don't need to explicitly provide a signature because, as I said, the signature from the transaction, from that address, will just be used to authenticate the user.
Awesome. Thanks.
No worries. Thank you. Bye. Good luck.
Yeah.
Thanks for the presentation. Thank you.
No worries. Thanks. Bye.